Hello students, welcome to the lecture number 10 on hydrocarbon chapter. So far we have discussed many topics in this chapter, and basically in the previous 9 lectures we have discussed different topics like preparation of the alkanes, then we have discussed the physical and chemical properties of the alkanes, then alkene, that we have discussed the physical and chemical properties of the alkene and also its preparations, and also we have discussed the different properties of the alkynes. And in the last lecture, in the lecture number 8, lecture number 9, we have discussed about the very important hydrocarbons, that is the aromatic hydrocarbons. And in that lecture we have discussed that what basically aromatic hydrocarbon is, that is a difference between the other hydrocarbons. In this lecture, that is the lecture number 10, we are going to discuss another very important thing, that is the aromaticity and the preparation of the benzene. Two topics we will going to discuss in this lecture. So heading of this lecture, that you can see that aromaticity and preparation of the benzene. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. See, benzene is a parent aromatic hydrocarbon, but its name is applied to other cyclic systems, that is aromatic, when they satisfy different norms, that is the different regulations that has been made, that they are basically that we are going to discuss. Number 1, first, that is the norms for aromaticity. You can see that is the norms for aromaticity. Norms, or we can say this is the rules for aromaticity. There are different rules that have been framed. Number 1 rules, that the molecule should be cyclic, it should be cyclic and it should be planar. The molecule will be planar. Why it is made planar? Because it is at the plane, because it is required when the aromatic we are talking about, it is basically the stable hydrocarbons. In spite of this fact, it is having the conjugate system, double bond, single bond, double bond, single bond. But in spite of this unsaturation, it is a stable one. So first thing, that is the cyclic and planar. Second thing, the conjugated systems. That is a requirement, conjugated system, that is a single bond, double bond, single bond, double bond. Third one, that is delocalized pi electrons. Delocalized pi electrons. And fourth point, that is very important point, that is called also the Haeckel's rule. Haeckel's rule. Haeckel's rule is basically that in this cyclic system, it should have the 4n plus 2 pi electrons. 4n plus 2 pi electrons. And at that time, when all those 4 criteria have been satisfied, at that time we will say this is a aromatic compound. But we will, with the discussion, we will observe different types of exceptions, and sometimes it will be looks like aromatic, but it is not aromatic, it is anti-aromatic, or sometimes it looks anti-aromatic, but it is become a non-aromatic. So all those things will be discussed. Now we will have some examples. With the example, this all the 4 points will be clear. This is benzene. Benzene is parent aromatic compound and it satisfies all the 4 points. It is having the 6 pi electrons which is totally delocalized, and you have seen the conjugation system: double bond, single bond, double bond, single bond. This is a benzene. And here, as per Haeckel's rule, is N equal to 1. When you put the N, you will find that it is 6 pi electrons. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, and single bond. And this is naphthalene. Naphthalene. Here you can say, you can observe, here N is equal to 2 and there is numbers of pi electrons. How much it is? It is 10 pi electrons. Okay. Now again another aromatic compound, very important aromatic compound that we are talking about, that is 3 rings. It is having 3 rings. Single bond, double bond, single bond, double bond, double bond, single bond, double bond, single bond, double bond, single, double, single, double, single, double, single, double, single, double. So this is anthracene. Anthracene. And here you can see N equal to 3. And here you can observe how many pi electrons? It is 14 pi electrons. 1, 2, 3, 4, 5, 6, 7. 14 pi electrons. All are aromatic compounds. There are some heterocyclic compounds you will find. They are also be aromatic. Whether by this, we will be talking about the heterocyclic compounds. Heterocyclic compounds, first we will discuss. That is heterocyclic compound. It is pyridine. This is pyridine. It is heterocyclic compound. Here also you can observe it is having 6 pi electrons. It is having 6 pi electrons. It is pyridine. And it is having 6 pi electrons. And they are following all these rules, norms for aromaticity. Then another heterocyclic compound, it is furan. Here also you can see there is a 6 pi electron. It is furan. Now here also you can see is here with the 6 pi electrons. Here this is thiophene. This is thiophene. This is thiophene. Here also you can see 6 pi electrons is there. And another heterocyclic compound is a very important heterocyclic compound, that is pyrrole. Here also you will find this is pyrrole, and it is having 6 pi electrons. It is also having 6 pi electrons. So all are aromatic compound because they are following all those regulations. This is cyclic, this is conjugated, this is planar, this is having the following the Haeckel's rule, right? So another compound that is we are going to discuss, that is cyclopropyl cation. Cyclopropyl cation. Here you can see there is a 2 pi electrons. This is 2 pi electrons, and they are aromatic. Why it is so? But here you can see one thing, there is no conjugated system, but it shows the aromatic property, but stability it will show. How? That we can easily understand. From the first cycle. Another thing that we must remember, that is the first cycle. First circle that will going to give you whether any compound is aromatic compound or non-aromatic or anti-aromatic. How? Because in the first cycle, that is concentrated on the MOT, molecular orbital theory, that we have already discussed in your molecular bonding chapter. So from this first cycle, you can observe, in spite of this fact, it has no conjugated system, it is still aromatic. How it is? Let us understand. When we go to construct this first cycle, at that time what we have to do, we have to invert all these vertices of this polygon, right? It is a polygon. Now here you can see it is basically based on the MOT, molecular orbital theory, which is based on the bonding molecular orbital, anti-bonding molecular orbital, another is no bonding molecular orbital. When the electron mostly present in the molecular orbitals, bonding molecular orbitals, it will be much more stable. But when it is present in the non-bonding or anti-bonding molecular orbital, in unpaired way, in the unpaired electron present in those anti-bonding and no bonding orbitals, and this is molecular orbitals, this is going to be unstable. That what we observe here, this is 2 pi electrons, and molecular orbitals, this is the lowest energy level, and this is bonding molecular orbital. This is bonding molecular orbital, and this is no bonding molecular orbital. This is basically we are talking about the energy level. This is no bonding molecular orbital, and this is your bonding, anti-bonding molecular orbital, anti-bonding molecular orbital. So when these 2 pi electrons will be present here in the doubly pair, as there is no electron in this no bonding molecular orbital, it is much more stable. In spite of this fact, there is no conjugated system. So it is not by which we can able to understand about the aromaticity, non-aromaticity or anti-aromaticity. So cyclopropenyl cation is the aromatic. Now we have discussed another 2-3 compounds which is aromatic. Then we are discussing, that is cyclopentane diaryl anion. This is cyclopentane diaryl anion. It is also the aromatic compound. How? Let us understand. This is cyclopentane diaryl anion. This is this, and here you observe total 6 pi electrons, and it is planar and it is completely delocalized and it is very stable. So cyclopentane dienyl anion is aromatic. Another compound that we are going to discuss, that is cycloheptane tetrahepta cycloheptatedinyl cation. It is also, you will find, it is aromatic. How it is aromatic? Let us understand. So here you can see DH is having the 6 pi electrons. It is 6 pi electrons and it is a planar. It follows the Huckel's rule, so it will be aromatic. Okay. So all those are aromatic compounds. So we can conclude, we can make a rule about this aromaticity, that we can write in this system. It is also called the Huckel's rule. Huckel's rule, or it is called 4n plus 2 pi rule. It says any cyclic planar system having 2, 6, 10, 14, 18 pi electrons and having one single cyclic electron clouds encompassing throughout the carbon atoms in the ring. So we call it is a aromatic. Okay, so this is all for the aromaticity. Now we will discuss some compounds. You will find that they are not stable, but they will follow all these rules, except one rule they do not follow, that is they have the 4n pi electrons instead of 4n plus 2 pi electron. Instead they will have 4n pi electrons. So at that time we will call it is anti-aromatic, and we will discuss some compounds. We are going to discuss the anti-aromatic compound. Anti-aromatic compound. The only difference between the aromatic and anti-aromatic is that it will having the 4n pi electrons. other conditions that we have discussed in case of aromaticity, it follows. That is, it will be a cyclic system, consecutive system, it is planar, it is completely delocalized, all the things followed. But only these things is not followed. That is why they are very much unstable compound. Example that we are going to put: this is cyclopropenyl anion. This is when it was cation. At that time it was the aromatic, but when it is an anion, it is become anti-aromatic. Now you see the difference, and this can be explained because it is having the 4n pi electrons, and this we have already discussed. Fourth cycle, the 2 unpaired electron will be put on the non-bonding zone, and that is why this molecule is very much unstable and it will become anti-aromatic. Another example that we are going to discuss, that is this is cyclobutadiene. Here also you will see the same thing, that is, it is having the 4n pi electrons. Okay. Similarly, you will have another example, and that will be very much give you the clarity. That is this is cyclopentadienyl cation. Here also you can see that there is a 4 pi electrons. This is 4 pi electrons. Here 4 pi electrons. It is also 4 pi electrons. That is why they are showing this body. Another example you can see. This is cycloheptatetraenyl anion. Here also you can see that how many pi electrons? That 8 pi electrons is there. Here you can say n equal to 2. So it will have the 4n pi electrons, so here is 8 pi electrons. So this is also anti-aromatic. Now one example that we are going to discuss, it will appears at the first level, that is, it is a anti-aromatic, but it is not anti-aromatic, it is non-aromatic. This example is this. This is compound name is cycloheptatetraenyl in. Cyclooctatetraene, and this is also called COT. You can observe there is 8 pi electrons. So you can straightway say this is anti-aromatic. But it is not, because due to some problem in the molecular arrangement, it takes the shape of this. It takes the shape of a tub. It takes the shape of a tub, and it is non-planar. It is not planar. What we have assumed that it is planar, actually it is not planar. So it is, you can say, non-aromatic, not aromatic. Anti-aromatic, it is non-aromatic because it is non-planar. So one variety we are going to discuss, that is the non-aromatic compounds. Sometimes question asks, we will give this compound and you will give him different options. Then you have to say which will be actual answer. Then the answer will be it is non-aromatic. So another example of the non-aromatic compound that we are going to discuss, it is cycloheptane cycloheptatetraene. This is non-aromatic because of this fact that it is having a non-planar structure. Due to this non-planar structure, what is going to happen? The pi electrons are not completely delocalized, and that is why the stability of the compound you cannot able to get, and they will resemble the chemical reaction of the alkene, like addition reaction, it will show the oxidation reaction. So it is no more a stable compound. So this is non-aromatic compound. Another example we are going to discuss about the non-aromatic compound. This is again a very important compound. This is cyclodecapentaene. Cyclodecapentaene. The structure of this is like this. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond. So this is cyclodecapentaene. Here you can see it is having the 10 pi electrons. So if we go by the Haeckel's rule, it will follow. It should have the aromatic property. It should be aromatic compound. But due to this non-bonded hydrogen, it will become a non-polar. It will become a non-planar. So due to this non-planarity, it is become non-aromatic, and it will show the reaction of the alkene. So we have covered the first part of this lecture, that is aromaticity. Why a compound is called aromatic compound, that we have discussed in detail. That is the 4 criteria. First, that is the planar, it should be cyclic, it should have a conjugated system, it should have delocalized pi electrons, and lastly that 4n plus 2 electrons. And in case of anti-aromatic, we observe that only difference is there, it will number of pi electrons is different, that is 4n pi electrons. And we observe in case of this cyclooctatetraene, which appears as anti-aromatic, but due to its structural deformation or structural change, it has become a non-planar, so it is become non-aromatic. Now we also discuss some non-aromatic compound also. The difference between the aromatic, non-aromatic and this anti-aromatic is basically this that we have discussed. It will have the 4n plus 2 electrons, 4n electrons in case of non-anti-aromatic, all other condition is same, and in case of non-aromatic it will have the non-planar structure. Due to this non-planar structure, the electron will not be delocalized, and that is why it will not going to be stable. It will going to show the reactions as being undergo by the alkenes. Now we have discussed the preparation of the benzenes. Benzene can be prepared. The first, that is the cyclic polymerization. Cyclic polymerization. In this case, we observe under a heated condition, when the ethane has been passed through a red or hot iron tube, and its temperature is normally being kept at 873 Kelvin. At that time, you will find this has been polymerized. 3 molecules of the ethane have been polymerized, and it will going to produce the benzene. The reaction is this. That we have already discussed during the property of the ethane. So its temperature is 873 Kelvin, and it is going to produce this CH2 double bond CH, CH2 double bond C, then CH double bond CH, and this. So this is, you observe, that is the benzene has been produced. So we can write also in this way. This is one process. Second process, that is the decarboxylation. Decarboxylation of aromatic acid. What is the reaction? Reaction is this. In presence of soda lime. Soda lime is basically the mixture of CaO with a 3:1 ratio, and when we heat it, it will going to produce benzene. Straight away we get the benzene and 8N2CO3. Okay. Third way, from the phenol. From phenol, when the vapor of the phenol is passed over the heated zinc dust, it is going to produce the benzene, and the reaction is this. So that is all for this today's lecture. we have discussed a very important topic, because from this topic you will get 1 or 2 questions in your NEET, JEE, 100%, because this is very important, interesting chapter, and different type of techniques questions may appear. So in this lecture we have discussed aromaticity, anti-aromaticity and non-aromaticity, and we have also discussed how we can able to prepare by different ways the benzene. That is all for today's lecture. We will come back to the another topic that will be the last lecture in this hydrocarbon chapter, that is the that will be discussed in the next lecture. Thank you very much for watching.